Locality of technical objects and the role of structural interventions for systemic change. To study the harms and ethical problems technology elicits, we may take different modes of inquiry. One methodological perspective studies inherent properties of algorithms, often in terms of their statistical performance, and ensures these properties align with legal and ethical concerns. For example, fairness and privacy constraints can be enforced through regularization. We explore a complementary methodological approach which views algorithms as embedded in a web of social relations. We focus on the roles algorithm-driven systems play within a specific social context by virtue of their position in a system. As we will see, the way algorithms relate to other social elements is at times more influential than their actual properties. Let us use as an example the case of lending. Assume a general population has been grouped according to racialized categories. Note these categories are not reflective of actually cohesive and well-defined social groups and have no biological basis. However, they are used for datafication and institutional decision-making. By creating these categories, group-specific credit score distributions and repayment probabilities can be derived. We want to know how the credit distribution pi, serving as a measure of a group's financial robustness, changes as the system evolves. In this scenario, an applicant exhibits a particular credit score assumed to be sampled from the population distribution. An algorithm is then used to decide whether to provide a loan or not based on a population-specific threshold. If the applicant repays, their credit score increases. If, on the other hand, the applicant defaults, their credit score decreases. The updated credit scores are fed back to the population's distribution, shifting such distribution over time. To explore the dynamics of the system, we examine the temporal evolution of pi, summarized graphically as a point in the mean and standard deviation plane. A desirable outcome concentrates the mass in the high credit score region. In an undesirable outcome, the score converges to the low regions. In the left column, when rho, a population's probability of repayment, is low, we observe undesirable convergence both for an unconstrained classifier and one satisfying fairness conditions. On the right column, if a population exhibits better economic resources for repayment, we observe desirable convergence even under unfair algorithmic conditions. This behavior is in part due to the persistence of factors existing prior to and external to the algorithmic decision-making process. For example, the withdrawal of economic, health, and infrastructural resources from a community, prohibitive access to education and job opportunities, and lack of a robust financial network and inherited wealth. Since these factors are not affected by algorithmic constraints, their influence prevails, and even when desirable feedback is drawn from the decision outcomes, it is limited in its effect to positively affect the system. These external factors remain as a driving force of harm. Ethical technologies are therefore limited to an extent by the impositions of structural elements. Furthermore, the data-generating mechanism interacts with other mechanisms, each of which has its own intricacies. For example, social technologies for data collection comprise a sampling mechanism in which individuals are datafied. In general, you can assume the sampling process to also involve social factors. For example, surveillance patterns by police and their decision to arrest or not an individual, as well as the features with which these individuals are represented, are all part of the sampling process for the case of the criminal justice system. These mechanisms produce data from which algorithms are designed under a certain paradigm, which then influences actual algorithmic deployment. The diagram exemplifies one such interaction among mechanisms and highlights the last two, whose interior workings are usually the focus of algorithmic fairness research. To understand this phenomenon in a cohesive framework, start by thinking of a system as a tuple composed of a collection of objects and relations among these objects. The objects include technological objects like datasets, classifiers, and automated bureaucratic protocols, as well as social agents. The relations among them determine the structure of the system. These relations can be, for example, the processes through which the state codifies its population into data points, the practice of redlining and segregation, direct discrimination, policing, and institutional hurdles. Two often encountered properties of relationships are those of modularity and feedback. Modularity can be thought of as an analytical assumption and basically encapsulates what we saw in the previous slide with the different mechanisms, that these mechanisms are separable into modules and can therefore be studied independently to a certain extent, but we acknowledge their interdependence. To provide a more specific example, consider the case of mortgage lending in the 60s and 70s in the United States. The diagram here is inspired by the book Race for Profit. Before decision-making takes place, there is a process of financial development in which economic resources, racist practices, and historical segregation interact to determine an individual's socioeconomic status. When these individuals enter the housing market, current government legislation and predictive tools are added to the process and a loan is given. However, new homeowners of underprivileged communities are not given the same social support to sustain their ownership as privileged communities do, leading to dire housing conditions and even total loss. Notice that the predictive tool, one of the nodes in the middle module, has the same position in the system, be it human or automated, fair or unfair. As explained in Race for Profit, even though fair lending procedures were in place, the whole system was so defective it drove many people into further poverty and harm. For another example, consider the case of incarceration. The details of the diagram will in general be different, but the principles are the same. Different social agents and technical objects relate to each other in a structured way, and these relationships constrain the position of such objects. Here we see again a predictive tool, which can be a modern machine learning algorithm positioned in the middle module. Now, consider a property of interest in our analysis, for example, a measure of global equality. If this is a systemic property not exhibited by individual parts of a system, we call it emergent. Other examples are institutional racism, which is not enacted by individuals, but by a series of social protocols and institutional hurdles. Or consider a distribution derived from a whole population, like the distribution of credit score in our lending case. With this in mind, we introduce the concept of locality, which broadly speaking means the effect of an object on the overall system dynamics is fundamentally limited by its position among a web of relations. If phi is an emergent property of interest, then under locality, phi remains the same for a system S containing the object O, and the system S prime identical to S except for the exchange of O for O prime. We already saw this phenomenon in our first example, where we exchanged an unconstrained classifier for one satisfying fairness, but for which the eventual convergence for low credit scores prevailed. Diagrammatically, we can think of it in the following way. Here we have a mock system. In the left, one object is replaced by another. In the right, the position of the object is modified, as well as how other objects relate within the system. We call the left intervention local and the right intervention structural. To test this framework experimentally, we go back to the lending scenario. The previous version was a simplified version to the one shown here, which allows us to pose a causal narrative and therefore obtain causal effects. The details can be found in the paper, but the general intuition of our simplified example remains. This figure shows the relative amount of high credit scores for both the Black and white groups. Over time, scores for the Black population get subsequently lower, even when fairness constraints are in place. On the other hand, for the white population, the amount of high scores remains relatively high. Notice that fairness considerations do improve over unconstrained deployment, and indeed, fair treatment can be life-changing for individuals. We're not saying they're not needed. We encourage their use. The message is that our social systems are so ill-structured that even under these considerations, there remains a robust inequality gap. We complement, therefore, these interventions with what represents in our simulations social restructuration. This image is the important experimental result of the paper. In the image, we plot the final convergence values for the amount of high credit scores for the different types of interventions. In the left cell, only the algorithm is modified, enforcing fairness constraints. In the middle cell, this is complemented by altering the data generating mechanism to allow for better score distributions. In this case, even if the bank uses faulty data, both populations eventually converge to a concentration of high scores. In the last cell, we keep the data generating mechanism, but support the population by modifying their ability to repay their loans. As we can see, intervening in structural elements has a larger effect on well-being and equality, and can also incorporate fairness constraints. We finish by providing a set of practical guidelines for design and assessment of algorithmic decision tools embedded in social structures. These guidelines are, first, reformulate. That is, shift perspectives from properties to systemic roles. This includes reformulating our most basic assumptions about our data. For example, the fact that racial categories, which are often encoded as one more variable in a feature vector, are not essential properties of individuals, but themselves systemic in nature. We point to the paper for a larger discussion on datafied categories. Second, identify both stakeholders and their relations. Identifying proper relations is often challenging, but of particular importance, as they form the basis of emergent properties, information flow, decision-making, and so on. Third, structuralize such relations. For example, provide hierarchies and power differentials. If possible, find causal connections, and formulate part-whole relationships as well as emergent properties. Finally, expand. Expand spatially by accounting for context and external factors, and expand temporally by including generating mechanisms as well as feedback and long-term effects. In summary, technology's effects on social systems can be studied under different frameworks. With the systems view, we can study technical objects in terms of their position and relations to other objects within a system. Local interventions are those for which changing an object is not enough to change the dynamics of the system. We compare these with structural interventions in an experiment using data from a lending system. We find that structural interventions are more effective in altering the converging behavior of the system. Finally, we provide a set of recommendations to implement this approach, the RISE framework. We believe taking this complementary perspective will allow us to better implement policy for lasting change. Thank you.